Exercise 3B, question 6e. We've got to see whether the given series is either absolutely convergent or divergent. It's an alternating series, so we're going to use the alternating series test. And at the moment, all I've done is I've noted that the absolute modulus of UK is equal to 2 to the power of k plus 1 divided by, in parentheses, 2k plus 1 factorial. In fact, we're going to end up using the squeeze theorem on this in this particular proof. So the first thing that we can notice is this will always be greater than or equal to 0. Can we actually get equality with the 0? Let me look. No, it's always going to be greater than 0. Okay, so let's see what we're going to do. The first thing is I'm actually going to say that this is always less than or equal to 2 to the 2k plus 1 over 2k plus 1 factorial. I just want that power to be the same as this value I have down here in the denominator, the 2k plus 1. And obviously the statement I've made is going to be true. The next thing to do is to list out what this actually looks like. So it will be, I'm going to write the factorial in reverse order actually. So 2 over 1, 2 over 2, and that will go on all the way up to 2 over 2k plus 1. And then I'm going to suggest that there's some value in the middle, 2 over m, where m is a value that is greater than 2. What does that mean? Well, if you think about it, it means that everything from here on down will actually be a fractional amount. Here I'm just going to write the term that came before. So I have this. Now, if I also have, I think it's fairly obvious that m is less than or equal to 2k plus 1, then in terms of all of the denominators that you're going to see going from here up to 2k plus 1, if they're listed out in order, m in fact will be the smallest value in any of those denominators. So I can now make the following claim, which is crucial to the proof. Okay. I'm going to say that I'm going from here, that this must be less than or equal to 2 over 1, 2 over 2, dot, 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 2 over m minus 1, dot, 2 over m, dot, 2 over m, all the way up to that last term, 2 over m. Sorry, it's not really a term, to that last part, 2 over m. Okay, now let's have a think. We can see that we have m minus 1 parts here. And so in this part there must be 2k plus 1 minus m minus 1, which are the parts we've used here. So in that case I can now say that here there must be 2k plus 1 minus m minus 1 m's in a line. Okay. Well, the next thing we're going to do is say that that therefore is, or the original is less than or equal to, I've still got 2 to the power of 2 to the k plus 1 divided by, well, for this part I'm going to say m minus 1 factorial, and then for this part it's going to be m to the power of 2 to the k plus 1 minus m minus 1. It's looking a little bit complicated, but hopefully you're going to see what we're going to do with this. Well, right now in fact I'm going to bring together the 2 to the k plus 1 and the m to the power of 2k plus 1 part, and I'm actually going to write that down as 2 over m to the power of 2k plus 1. Let's see what I've got left. Well, I've certainly got this m minus 1 factorial here, but I also had an m in the denominator, an m to the power of minus m minus 1, which hopefully you can see will just become m to the power of m minus 1. Okay, now what we're really interested in then is the following. We're interested in the limit of this as k goes towards infinity, and hopefully you can see that this part here in fact is just going to be a constant. We've already defined that m is greater than 2, so as k goes towards infinity this is essentially a fraction, and hopefully you can see that that's going to go towards 0. Now what we're going to claim then is the following. We've got 0 is strictly less than the expression that we started with, which was once we've taken the absolute sign, of course, this which itself is less than or equal to 2 over m to the 2k plus 1 times by m to the m minus 1 over m minus 1 factorial. And then we're simply going to use the squeeze theorem on this. So we're going to say as k tends towards infinity, we know that obviously 0 is 0, but on the other side we've got 2 over m to the 2k plus 1 times by, I'm just going to call that the constant p rather than write it out again, and that will equal 0 times by p, which will equal simply 0. So we've got this here squeezed between two limits that tend towards 0. So we can simply say by the squeeze theorem the modulus of uk in the limit as k tends towards infinity equals 0. So that's the first part of the alternating series test completed. We now need to show that the absolute value of uk plus 1 is less than the absolute value of uk for all k under consideration, which are of course the positive integers. So if we start off, I've written in blue what uk looks like, that's just for reference. If I start off with the absolute value of uk plus 1, I get this expression. So I'm going to rewrite this now and say that is the same as 2 times by 2 to the k plus 1, and underneath I'm just going to for now write that down as 2k plus, well 2 times 1 is 2 plus 1 is 3 factorial, and that itself then equals 2 times by 2 to the k plus 1 over, okay, that's 2k plus 3 times 2k plus 2 times by 2k plus 1 factorial. So now what I'm going to do is say that this is the same as 2 over 2k plus 3 2k plus 2 times by 2 to the k plus 1 over 2k plus 1 factorial, which of course is uk. So I've now got that that's equal to 2 over 2k plus 3 2k plus 2 times by uk. Now the question is this smaller than uk? And the answer I think is fairly obvious. If we look at the fractional part, so considering 2 over 2k plus 3 2k plus 2, well 2k plus 3 is greater than 2 for all values of k that are positive integers. Furthermore, 2k plus 2 is also greater than 2 for all values of k which are positive integers. Therefore 2 over 2k plus 3, 2k plus 2 must always be less than 1. The denominator is obviously bigger than the numerator, and therefore we've determined that when we have this expression here, that must be less than 1 times uk, which is of course uk, and therefore it will be strictly less than as well, of course. I've now shown that uk plus 1 is indeed less than uk, and that essentially completes the alternating series test in this question. I'd probably just write a nice little sentence or two at the end to tidy up my arguments.